Hello, my name is Luis Roldao and I am going to present our work on lightweight multiscale 3D semantic completion. In this paper, we attack the task of semantic scene completion from a single sparse LiDAR scan, producing a complete 3D voxel representation of occupancy and semantic labels for the 3D scene. This task can be of great interest for mobile robotic applications, which will enable to deal with the limited field of view, sparse sensing, and occlusions that are commonly present in outdoor LiDAR scans. To tackle this, we introduce LMSCNet. Our architecture achieved state-of-the-art performance while being significantly lighter, thanks to a mix of 2D-3D convolutions. For this, we introduce a novel 3D semantic scene completion pipeline from occupancy grids, which is modular and enables multiscale predictions at faster inference times. This is useful for real-time applications such as autonomous driving. We now present the architecture in detail. The goal of the task is to assign a semantic label C to each individual voxel in the output, considering n semantic classes and an additional class to represent free voxels. All of our choices were done by targeting a lightweight architecture capable to perform real-time inference. Different from the literature, we rely solely on 3D voxelized occupancy data, avoiding any preprocessing such as gradient distance functions or GSDF, which require a greedy computation time and bring small benefit. We use a standard encoder-decoder unit architecture with multiple scales. Instead of greedy 3D CNNs, we use a mix of 2D-3D convolutions to prevent heavy computation overhead. The backbone of our unit is formed by 2D convolutions performed along the XY dimensions, thus turning the height dimension C into a feature dimension. Notice that we directly process 3D data in contrast to other 2D-3D works that rely on 2.5D data such as depth or bird-eye view. While using 2D convolutions imply losing 3D spatial connectivity, it also enables significantly lighter operations. To further reduce the memory requirements, we keep a low number of features in each convolutional layer. Along with the standard skip connections, we also enhance information flow in the decoder by concatenating the output of each level to all lower levels of the unit. Technically, we upsample coarse feature maps, learning ad hoc the convolutions before the concatenation blocks. Intuitively, this enables our network to use high-level features from coarser resolutions, and thus enhancing high-level spatial contextual information. To predict the completed semantic scene, we introduce 3D segmentation heads at each output scale, enabling to retrieve the full geometrical semantic information. In details, the segmentation heads use a series of dense and dilated convolutions. Dilated convolutions are implemented in the form of 3D through spatial pyramid pooling blocks, or ASPP, which are beneficial to fuse information from different receptive fields thanks to the variable dilation rates at no cost. Note that the dilated convolutions are not appropriate for sparse inputs, and as such cannot be used in the encoder of the network. These 3D segmentation heads are designed for three specific reasons. To retrieve the third spatial dimension that was lost on the 2D backbone, this will enable the prediction of the completed semantic scene, and finally to ward off or separate the similarity between features on the 2D backbone and the segmentation heads, which is fundamental to enable multiscale capacity. Through the use of separate segmentation heads attached to the end of each output scale, we are able to predict the scene at 4 different resolutions in our multiscale architecture. This enables inference at desired scale as needed in a coarse-to-fine prediction scheme. The network is trained end-to-end from pairs of sparse input voxels and semantically labeled grids at different scales, encoded with hard labels. For each scale, we use a cross-entropy loss to predict a continuous distribution of semantic classes for each voxel. Soft labels for low resolutions were tested by using KL divergence loss without showing any improvements. Since semantic tasks are highly imbalanced by nature, we account for this by weighting each class loss according to the inverse of its frequency. The complete network loss is a weighted sum of all level losses. After experiments, we weight all equally to 1, which works well and preserves multiscale capacity. We train the network using the semantic kitty dataset that has been recorded by using a Velodyne LiDAR of 64 layers. We use the official train validation and test splits. Notice that the ground truth is semi-densely annotated, since complete annotation is impractical for a real setup due to occlusions and limited field of view of the sensor. For such reason, ground truth is labeled with n+2 classes, including free and unknown voxels. For the supervision, we use a sparse loss strategy by backpropagating the gradient only where the ground truth is known. Moreover, dynamic objects in the scene create incorrectly annotated data due to the stack of many scans for the ground truth creation. We compare our network against other approaches presented for the semantic scene completion task. We measure the memory and computation needs along with the inference time for all networks. It can be observed that for full resolution predictions, our approach is the lightest with the less memory and computation requirements. Inference time is doubled by the LMSCNet variance, which is caused by the higher number of sequential operations in our network. The interest of our multiscale capability can be highlighted by seeing the lower part of the table. Inference at lower scale can be done considerably faster, at less than half of the time of LMSCNet, and memory and computation needs can be reduced even further. We now present some qualitative results on Semantic Kitty and compare against the LMSCNet baseline. Notice that our network performs more precise and smooth predictions. Taking a look to the ground truth also illustrates the sparse supervision complexity, since holes are still visible. It can be seen also that predictions of the network are even denser than the ground truth, filling missing information. We now present the multi-scale capability of our network, with the predictions at multiple scales and their inference times highlighted. Our network is capable to predict precisely the scene at all required resolutions thanks to our supervision on all scales. The following plots represent the trade-off between performance, speed, and memory requirements. The number of parameters of the networks are scaled by the marker size. Performance in occupancy completion and semantic scene completion on Semantic Kitty are reported. Ideally, the best network will be the one with the smallest marker size in the top right section of the plots. Notice that our network shows the best trade-off with high performance in both metrics, small number of parameters, and fast inference. We now report quantitative results on the hidden test set of Semantic Kitty. Overall, our network performs on par with best methods, achieving state-of-the-art performance for semantic scene completion and improving results for occupancy completion, where our network outperforms all others by a comfortable margin. TS3D variants use additional RGB modality or LiDAR reflectivity signal. Despite one of these variants achieving a slightly better semantic scene completion performance, the network is considerably heavier and slower than ours. Notice that our results are also better than faster LMSCNet variants. We outperform all networks on the largest 4 classes present in the dataset. We also report results for LMSCNet single scale, a variant of our network that has been trained for predictions on high resolution scale only, improving results at the cost of losing crucial multi-scale capability. We test the robustness of the network against lower density inputs by subsampling the input 64-layer LiDAR of Semantic Kitty. 32, 16, and 8-layer subsample input scans were obtained. At the right-hand side, performance from 8-layer LiDAR input can be seen. Notice that even at extremely low density, the network is still capable to correctly predict the outline of the scene. The plot in the middle shows the quantitative performance drop in function of the LiDAR density. We also test the transferability learning of our network by training on Semantic Kitty with 64-layer LiDAR input resolution and testing on the 32-layer LiDAR new scene dataset. The high vegetation prediction on new scenes can be explained by the more residential and suburban scenarios present on the training data of Semantic Kitty. Despite this, the network produced acceptable outputs with a good outline prediction. We validate the configuration of our architecture by different ablation studies. We refer to the article for further details. Thank you for watching. We invite you to read the article and to check out our code that has been released in open source.